So what we can do here is we can still do the same thing we did before. We need to change it into a limit. So we can do the limit as a goes to infinity, and then we could just have from what to what?
0 to infinity.
No, to make it the same as this, though.
Negative a.
So we'll go negative a to positive a. And then that'll take that one limit. We'll take our lower limit to negative infinity and our upper limit to positive infinity. So now the question is, doing this antiderivative, great practice for, so we need to identify and figure out what we need to do. Okay, so how are we going to do this antiderivative? Is it always, the first question is it undoing the chain rule? Is it undoing the chain rule? So what would be there's one of two changes we could make. So it would be undoing the chain rule. What would be one of those? Yeah.
Yeah, undoing the chain rule, and we separate the two terms, and it looks like the arctangent.
No, but it's not undoing the chain rule. And so what I'm asking is, how would we alter this to make it undoing the chain rule? What's one way we could do that, Christiana?
You could change the x to the 6 to x to the 4.
X to the would be to the fourth? Third, right? If this is 3x squared, right?
Or you could change 3x squared.
So if this were x to the third, then we'd have undoing the chain rule because your derivative's up here. And the other possibility would be?
Change x squared to x to the 5th.
This would be x to the fifth. Okay, so again, always on the lookout for undoing the chain rule. It's always your first line of defense on these harder antiderivatives. So this doesn't work for that. But he was onto something over here. Notice what we have. We have 1 plus x to the 6th. So we have to kind of recognize what is that kind of like. Arctangent would be 1 over 1 plus x squared. So if we could do a change of variables and make this u squared, so we want x to the 6th to be equal to u squared. So we're asking what would u have to be so that was true? X to the third, right? You take the square root of both of those. And so then we do du equals 3x squared dx. And then always look, lo and behold, what do you see? There it is, 3x squared dx, which is the same as du. So sometimes you don't have to solve for dx and put in what you get for dx just into dx. What you get for du will be part of your integral. So always be on the lookout for that. And then it makes your life a lot easier. You can observe that 3x squared dx is the same as du. Then you have it. So we do the limit. Now, as, say, so we'll change it back to x. So we're just doing this for now. We're just doing this antiderivative. And then we'll switch it back to x and recapture our limit and our limits of integration. So what do we have? We have just du over 1 plus u squared equals arctangent u. So this one's totally rigged to be a change of variables to u, and then we got arctangent u. Now we're going to switch that back to, so we have arctangent x cubed, and then we're going to evaluate that from negative a to a, where we're taking the limit as a gets really big. So from here, you just have to know something. So we're going to have limit as a goes to infinity of arctangent a cubed minus arctangent of negative a cubed. So now you just have to understand the arctangent function. What is the arctangent function? Well, it's the inverse of the tangent function. So what is the tangent function, first of all? What goes in and what comes out? Or what's our independent variable and our dependent variable of arctangent? So you think about the unit circle. So what does arctangent represent? What relationship is that? Yeah, John.
So you put in like an angle measure,
Angle measure, good.
and then you're basically going to get the slope on the like at each point. On
Right.
that.
Good. So if we had arctangent of, say, theta, tangent of theta means you put in an angle on the unit circle, and you get out tangent theta is the slope of the terminal side. Okay, and so what about the arctangent? Well, the arctangent then is reversed. So for arctangent, we're putting in what? We're starting with what? Slope, and we're coming out with angle. Okay, so arctangent gives an angle measure for a given slope. That's what arctangent does. It gives angle measure on the unit circle for a given slope. Well, there's a problem with that as a function, right? Because there's, for a given slope, there's lots and lots and lots of angles that achieve that slope, right? So we have to, for arctangent, we have to restrict the domain, so we restrict the range of arctangent so that there's, for any given slope, there's only one angle measure that comes out. So what is a range of angles that hits every possible slope just once? What is the range of angles that hits every possible slope just once? So what that is say negative pi over 2, close to negative pi over 2 is huge negative slopes, okay? And then as we move towards 0, we move towards 0 slope, and then as we move to positive pi over 2, we get really big positive slopes. So by restricting the angles, what can come out of arctangent from negative pi over 2, we get just one angle for every possible slope from negative infinity to positive infinity. Okay, so now what are we saying here? So if we're taking a to positive infinity, we're saying what? Let the slope get really, 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 really large, and we're saying what angle is that, the limiting value of the angle as the slope gets really, really big. And then same thing here. Now we're going to let the input here is going to be the slope. The slope is going to get really, really, really big negative. And so then what angle will this approach? What will be the limit of letting the slopes get really, really large negative? Okay. So then I'll let you finish the problem. So we don't do the whole thing, but you can finish it from there. So basically, again, what we're saying is let the slopes of these terminal sides of these angles get really, really large positive. And arctangent is saying what's the limiting value of the angle that you would get when you do that. All right, same thing with this. Let those slopes get really, really big negative. What's the limiting value of the angle that you would get when you do that? So I think I almost did the whole problem for you. So you just had the last little step. Yeah?
Do we have to write a range restriction somewhere in the answer?
No, because it's asking for this limit. You just have to know that stuff to evaluate this limit. So all that stuff, that range restriction, you have to know that about arctan in order to evaluate this limit. But this limit is either going to be undefined or it's going to be a value. Yeah.
So for the test then, would you like us to make sure that we, like when we're anti-differentiating, that we know the specific name of the different techniques, and like we can be able to label it? Does that make sense?
Yeah. So, yeah. Yes, you have to know the names of them in order to talk about them. So to do them. So
No,
yes.
that makes sense.
Yeah. Sure. Definitely. Yep. You bet. Other questions about this problem? Did it help? Okay, so that was good because so we know how to do now the limit. If it's all x values that we're accumulating over negative infinity to infinity, we got to take care of that, and then this is a nice change of variables example for arctangent. Okay. Any questions? Get out a sheet of paper. Yeah, I'll make the writing a little bit bigger here. Okay, so I have this function here, or y equals 4x over x plus 1, x greater than 1, and I'm showing that here in the graph. And I'm telling you that as x approaches infinity, y approaches 4. Okay, as x approaches infinity, y approaches 4. So I want to know. Okay, so here we go. Let's go over it. Grade your own. Ready? If you can get something, if you have something different to write with, that would be good. Something else different to write with. Okay, it's first thing. Number 1. So this y equals 4x plus 1, what is that relative to this expression? What is that 4x plus 1 equation, which I'm showing down here? What is that when we put it in an integral like that, then? It's a rate of change function, right? It's a rate of change function. And what's happening to the rate of change? It's essentially 4 for large values, right? It's going to get closer and closer to 4, and then as x gets really big, it's just essentially going to be 4 forever. So then what do we think about this then? Converge or diverge? If this is essentially a rate of change of 4 forever, then what are we doing? This is going to calculate what? The total change starting at 1 to infinity when the rate of change is essentially constant at 4. Is that going to converge or diverge? Diverge. Because for every, so what does the rate of change of 4 mean? It means for every unit of x, your quantity goes up by 4. Every time x changes by 1, your quantity goes up by 4. So x is just going to keep changing, x is just going to keep increasing, and every time x increases by 1, for large values of x, your quantity is just going to keep going up by 4. So what will the quantity function look like? You know, it's basically going to look like this. Right? Because it's going to keep, the quantity will keep increasing at a rate of change of 4, essentially 4, when x gets big enough. So when x gets really big, it's just going to be close to 4 and get closer and closer to 4. So that's the reasoning behind number 1. Does that make sense? Okay. What does it take for an improper integral, one that's, we're going to take x to infinity? What does it take for that thing to converge? First of all, what has to be true? Your rate of change has to do what? Has to go to 0. The only possible way that a improper integral of this type could converge is if that rate goes to 0. Right? So that in the end, you're essentially adding very, very little so that your quantity levels out. See, this isn't the quantity, this is the rate, right? We need the quantity to level out, and the only way that's possible is if the rate goes to 0. Is that enough, that the rate goes to 0? It also, it's necessary that it goes to 0, but that's not enough. It has to go to 0 fast enough. We saw an example, or there's lots of examples, where the rate goes to 0, gets very, very close to 0, but still the quantity just grows indefinitely because the rate at which the rate gets to 0 is too slow. Okay? All right, but this one definitely diverges because your rate of change is just leveling off at 4, so your quantity is just going to keep growing at a rate of 4. Yeah?
Would it be wrong to say that the rate function converges to number 4, but the quantity diverges?
That's exactly right. The rate function, and I told you that, right? That this is saying that the rate function converges to 4 units per unit of x. Yep, the rate function converges to 4. But because of that, then your quantity diverges. Okay, so now how do we do this? We want to show that this is a divergent integral, so we need to do the antiderivative. And there's actually 2 different ways, so we know, maybe 3, But there's two ways I can see that we could approach this. 4x over x plus 1. How do we get the antiderivative of that? Great practice for the exam. What technique can we apply? Is it undoing the chain rule? Nope.
Use substitution. X plus 1.
Okay, so we can do a change of variables. If you do u equals, I'll do that way first. If you do u equals x plus 1, then du equals dx. And we're going to need what x equals, right? X equals then u minus 1. So this is a good way to do it, and we'll get, what, 4 times u minus 1 all over u du. And how can we solve that?
You gotta change your limit.
All right. So I'll just, in the u, I'll just leave the limits off. We'll change back afterwards. So how do we do this? This is essentially 4u minus 4 all over u. And that's easy as long as you know what to do. We've seen this before. How do we do that? Okay, split them up, right? So this, we just split it up into 4u over u minus 4 over u. So we get 4 minus 4 over u, and now it's a piece of cake, right? 4, so that's going to be 4u minus 4 ln of u. And so then we can change that back to x. U is x plus 1, so we get 4 times x plus 1 minus 4 natural log of x plus 1. Absolute value is optional here because of the limits of integration. X is always positive, so that will always be positive. And now we're going to take the limit as x gets really, really big of this, right? So our limits of integration are going to be 1 to a, limit as a gets really large, 1 to a, and then all we need to see is this very first term right here. This is all we need, 4x, right? 4x is going to be 4a, and as a gets really, really large, 4a gets really, really big. So that confirms what we said in number 1, that the quantity just will get very large at a rate of 4, right? So the limit as a goes to infinity of 4a. And there's no minus 4a to get rid of that, right? So 4a plus 4 minus its natural log. I guess we have an issue here. Because this gets large too. 4 natural log of a plus 1, that gets big too. So what do we do with that? So I'm going to jump the gun here. Yeah, it does. So we had to show that mathematically. All right, so we got 4a plus 4 minus 4 natural log of a plus 1. And how do we do that? So we have infinity minus infinity. Indeterminate form. So can we get that into a form of a fraction? Can we get that infinity over infinity? What do we do with that? Do you know how to do this?
I'm trying to remember, but somebody had an
Yeah,
idea.
suggestion, yeah?
Could you perhaps try doing the undoing the product rule first and see what happens?
Well, we have the antiderivative. That's to get the antiderivative. So we're good with the antiderivative. We're running to is here with the limit, because this is going to get really big, but this minus, this is also going to get really big. So that's what's called an indeterminate form. Infinity minus infinity. So in certain situations, that might be 0. That might be a constant. That might be infinity. We know here it should be infinity, but the question is, we need to show that mathematically. Yeah.
So you take 4 off
Okay.
each term.
Yeah.
You get a minus 1 minus a plus 1 minus natural log a plus 1.
Okay.
A is bigger than natural log.
Yeah. So we know that a gets bigger than natural log of a, and that it's infinitely bigger.
Yeah.
but that's not really formal mathematical proof. Like,
Because you take the,
Is it ln of x minus ln of another term is divided by each other? So
no, you have it backwards. So it's ln of a sum doesn't. There's no formula for ln of a sum. The ln of a product is the sum of the ln's. So you have it reversed.
Matrix
Yeah.
exponential.
what if you treated them both like functions and then proved that one rate of change was greater than the other rate of change?
Maybe. But anyway, so this is yeah. So I have to get back to you on that. But
I think you can use an exponential.
what's that?
Like e to the 4a plus 4 over.
Oh yeah, and then factor out e and then put it in the bottom. Then you can use loop it all.
Would that work?
What is it?
Then you would get a to the 4.
I don't know. I know what you're saying. That's the first step.
So you say e to that.
The whole thing.
I'm not sure if it's gonna work though, especially with the 4.
Okay.
And you got a 4 in front of the natural log.
Okay.
And you're taking the limit of that expression.
Okay.
The limit will only affect the exponent. So you can turn that into a quotient, right? E to the 4a plus 4 over e to the,
And then do L'Hopital's rule.
yeah.
Nice. Okay.
But
Yeah,
also
that's
they'll
it.
simplify to a plus 1 to the 4.
So e to the 4a plus 4 over
A plus 1 to the 4.
e to the 4 ln of a plus 1. And then
Well, first simplify it.
don't I have to apply it to e first and then simplify it?
The natural log there, though.
So this is 4a plus 1. And then L'Hopital's rule, that's much bigger than that. Okay, so that was how we show that this thing actually goes to infinity. You raise the whole thing to the e, or e to that whole exponent, and then use the laws of exponents to get it to look like this, and then this, and then now we've got infinity over infinity, which we can use L'Hopital's rule, which will give us this thing over 4. L'Hopital's rule would essentially give us 4 times that over 4, and that clearly goes to infinity.
Good enough.
Does that work? Okay, other questions about this example? Oh no, so we want to talk about the other way to do this antiderivative. Does anyone have another way of getting the antiderivative besides u equals x plus 1? Yeah?
Well, is there a way you can do it by, I guess, by parts, where you just even
Yeah, parts might work. Parts might work. It's not a common form for parts, but it might work. Yeah. Did you try that? Did it work?
I did, and I had to consult for some other things, it got really complicated.
Yeah, so I'm not sure if it does or not. I don't want to try.
Yeah.
Okay? It might. But there is a way I know for sure works that's different than substituting u equals x plus 1. Did anyone? What kind of function is this? Rational, remember? And what technique did we have for rational functions? Yeah, so remember we had our parts, and then but the first thing we did is if the degree of the numerator was greater than or equal to the degree of the denominator, what could we do? Remember? Long divide. Remember this? Long divide. So this one is a candidate for long division. And it's a quick long division, right? So you need 4, so 4 times x plus 4 over, so that's going to subtract to 0, minus 4, and what do we get? So we get this thing equals 4 minus 4 over x plus 1. Simple. So that's easy. And that's the same antiderivative we got before. 4x minus 4 natural log x plus 1. So those are the two ways that popped out to me. You could do u equals x plus 1, and then you would have just u in the denominator. You could break up the fractions, or this is a candidate for long division. Either way, you get the same antiderivative. Any questions on the quiz? Yeah?
Do we have some L'Hopital's rule for the test at all?
Yeah, so you should. We did see it earlier. We did see it. When did we see it? We've seen it once this semester. Yes. If you have a limit, well, it's not going to be half the test. It might be one part of one question. You're not going to fail the test because of it. All right, so basically, if you have this indeterminate form, infinity over infinity, L'Hopital's rule says you can take we'll go over it really fast. It's not hard. If you're trying to take the limit and you get a infinity over infinity situation, if f and g both get very f and g, then what you have is called an indeterminate form, infinity over infinity, and that's L'Hopital's rule, which says if you take the derivative of f divided by the derivative of g, that limit is the same as this one. So this limit equals the limit of the derivative of f over the derivative of g. Notice that's not the quotient rule, right? The quotient rule is something much different than that. We're not taking the derivative of the whole quotient. We're applying this rule that says if you take the derivative of the top divided by the derivative of the bottom, that resulting fraction will have the same limit as your resulting fraction, as your starting fraction. And that can help you solve for it. Yeah?
What's the name of this rule?
L'Hopital's rule.
I think you can solve the 4x over x plus 1 by doing partial fraction 1 over with a over 1 and then b over x plus 1.
But you don't. No, you can't because you don't have a fact. This doesn't factor. This needs to have at least partial fractions means you have different. You have your denominator can be factored, and this is only one factor, so you can't really use partial fractions. I mean, I guess you could do what, like a plus b over x plus 1.
A over 1. Because then you'll get negative.
Okay, right, yeah, which turns out to, yeah. But normally we don't really embark on partial fractions without having at least two factors in the denominator. But I suppose that would work in this case. I don't know if that always works. Yeah, so there's fractions that can't be decomposed. So you can't always assume that this is true, is that what I'm saying. If you don't have a factorable denominator, it doesn't necessarily break up into two fractions. Okay. Other questions? Yeah.
Does L'Hopital's rule also work if they both, like if you end up getting like 0?
Yep. Also 0 over 0, right? So if it's 0 over 0 or infinity over infinity, it works for both those cases. That's right. Yep. Other questions? Okay. Give yourself 20 out of 20 on the quiz. And then hold on to it for your notes. So remember to make a column.
Because I didn't realize there were two.
So I'll just, it's up to Jason to put a column in the grade book and give you 20s. So you can remind him, okay? Make sure he puts a column in the grade book, Q912, and you get 20 out of 20 on that, okay?
I take bribes.
Okay. Save your bribe. He has to do this.
I'll listen.
Okay, so let's look at one more. Here's another one. Here's a rate function. Y equals 30 natural log x over x squared. And we're going to say for x greater than 2. So if this is the rate function, I'm showing you the rate function here in blue. Does the following expression, is it convergent or divergent? Is it convergent, without doing any math, is it convergent or divergent? Convergent?
Exponent of x.
Everyone wants, that's everyone's answer? Anyone have a different answer? Divergent?
I think it's a faster than x squared.
Isn't it?
Okay, so this is, notice this is not of the form 1 over x to the p, right?
Yeah, I guess it's not 1.
So this is not, it's not one of these. It's natural log of x over x to the p. So this, you can't apply that, you know, our rule for this is that if p is greater than 1, if it looks like that, it's convergent. We don't have that. We have natural log over x squared, so we can't use this rule. So ask my question again. Is it convergent or divergent?
We don't know.
Thank you. What is it?
But we don't know.
We don't know. It goes to 0. Maybe. Maybe it is, because it goes to 0. But does it go to 0 fast enough? The only way we know that fast is if we have one of those, 1 over x to the p. We don't have one of those. We have natural log over x squared. So maybe, but we don't know for sure. Okay, so let's find out. So we got natural log x times x to the minus 2. Antiderivative. What technique do we need? This is our undoing the product rule. Undoing the product rule, right? And so we've got our, remember this? F times g equals integral of fg prime dx plus gf prime dx. And so we want to pick what is our f and our g prime. So here's the deal. If we pick g prime to be natural log of x, what's the antiderivative of natural log of x? No, it's not 1 over x. Antiderivative. Antiderivative. It needs, you do that, you need undoing the product rule. So that forces you to put the natural log of x here. And put the x to the minus 2. So Adrian was right. We're going to put the natural log of x there. F prime is 1 over x. G is negative x to the minus 1. So our answer integral here, plus, it's good review, right? We haven't done this in a while. It's going to be now g, negative x to the minus 1. Oops, I have a 30 here. Let's stick the 30 on the f. And then this will be 30 over x. Okay, so our gf prime will be negative x to the negative 1 times 30 over x dx, and that will equal f times g, 30 ln of x over negative x. Remember doing this? So we're rewriting, we see that 30 ln x over x squared is one of the terms of the product rule. The other one would be negative 1 to the minus x times 30 over x. And that equals our f times g. So our answer is going to be this thing minus this thing. So 30 ln x over x, negative, minus, okay, antiderivative. This is 30x to the minus 2, basically. Negative, right? We got all kinds of negatives here. So this is negative 30 over x squared. But we're subtracting that. And then we have the negative from the antiderivative. So we're going to have x to the minus 1 again. And we're going to have, I think, positive 30 x to the minus 1. Is that right? So negative 30 x to the minus 2, but we're subtracting that. Minus 30 over x. Okay, and then we're going to evaluate that from what? 2 to a, and it's going to be the limit as a goes to infinity. Check my math, make sure I'm kind of going fast, make sure I don't make a mistake. So limit as a goes to infinity. 30 ln of a over a minus 30 over a plus 30 ln of 2 over 2 plus 30 over 2. Am I good or did I make a mistake? Let's see if I made a mistake. Okay, so now we can evaluate the limit. This thing goes to 0. This doesn't care what a does, it's just itself. Okay, this one is L'Hopital's rule, because natural log of a goes to infinity, a goes to infinity, so we can rewrite this one as negative 30 over a over 1. And this will have the same limit as that. I took the derivative of the top divided by the derivative of the bottom. And so that does what? Also goes to 0. So what does this thing equal? 30 ln of 2 over 2. Conclusion about the rate function? No, yeah.
Can you go over that part again real quick? Where you use the 30, if the L'Hopital.
This, L'Hopital's rule. Derivative of this would be negative 30 over a, and derivative of a would be 1. So now it's the limit as a gets really large, basically of negative 30 over a again. Who was asking that? You see it? So this one goes to 0 by L'Hopital's rule. That one goes to 0. And we're left with the quantity, the total quantity, 30 ln of 2 over 2 plus 15, 30 over 2. Conclusion about the rate function. What's the conclusion about the rate function? It goes to 0 fast enough for the quantity to converge, right? So we actually did the math and got a finite value for the quantity, meaning that the rate function, it does get to 0 fast enough for this thing to converge, because it converges to this value. Yes, yeah.
When we have 30 over a,
Uh-huh.
is that not in the same form as 1 over x to the p? Is it just because a...
But 1 over x to the p is the rate function.
Oh, okay.
That's just one term of the antiderivative.
Yeah.
1 over x to the p is just the rate function.